Alright, so from the last video, what we try to do is that we're going to try to prevent this mistake of rejecting the null hypothesis when it's true by adjusting the significance level, which we call alpha. So what alpha is that's the probability that we set ahead of time to try to not accidentally reject the null hypothesis. So again, if you're doing a medical study, you want your alpha to be a 1% chance that you reject the null hypothesis when it's actually true. If you're doing something that has to do with opinions, or you're looking at more human error involved, maybe you want it to be higher, to be like 10%. Usually, for a good rule of thumb, we do 5%, especially because that 5% kind of relates to 95%, which is the empirical rule, which will come up later. So again, don't forget the significance level, which will be on your final exam, so make sure that you guys know what this is the probability of making the mistake of rejecting the null hypothesis when in fact the null hypothesis is true. So for example, in our coin example, this would be if we had rejected H naught when it was true, so in the context, here's what that means. Saying a coin was unfair when really the coin is fair. Okay, so let's look at another example. So we're testing the claim that we're testing someone who claims to have ESP, that's extrasensory perception, that's like psychic, by having that person predict whether a coin will come up heads or tails. The null hypothesis is that the person is guessing and does not have ESP, and the population proportion of success is 50%. We test the claim with a hypothesis test using a significance level of 0.05. Now what we want to do is describe the significance level in the context. So, the null hypothesis is that the person is psychic, or is not psychic. Is not psychic. Okay, the alternative is that the person is psychic. So, if we accidentally reject this hypothesis, not ESP, then what we say is that the person has ESP. So if the significance level is 0.05, here's what that means. There is a 5% chance of saying a person. Now remember, if we mistakenly reject the null hypothesis, that means that we're saying something about the alternative hypothesis. So if you reject this one, then you're accepting this one. So we're saying a person is psychic, psychic. So there's a 5% chance of saying a person is psychic when really, so we rejected H naught, which means that we said they have ESP, but we were wrong, so they don't. So we want there to only be a 5% chance of this happening. Now, to make sure there's only a 5% chance of that happening, what we are going to use is something called the test statistic. Now, what the test statistic is going to do is it's going to compare the real world with our null hypothesis. Okay? This test statistic called Z is very similar to the z-score. So what we do is that we take our sample and we compare it to our null hypothesis, and then we divide by about how far off we expect them both to be. Okay? And how far off do we expect them to be? Well, that's going to be the standard error. Notice in both of these we use p naught. So that value that comes from the null hypothesis. So for example, say that we spun a coin 20 times and 7 times that coin comes up heads. Our null hypothesis is that p equals 0.5. Okay, and we want to find the z-test statistic and write a full sentence interpretation. So I'm going to give myself a little bit more room. So first off, z equals p hat minus p naught over se. So here's the ingredients we need. We need p naught, which is this value right here. We also need the p hat. Okay, well, it said we spun it 20 times and 7, it came up heads, so that's going to be 7 out of 20, which is going to give us 0.35. And then we also need to find our standard error. So we're going to use this formula here, and that's going to be the square root of, remember, it's p naught, so it's whatever value we saw in our h naught or our ha, so that's going to be 0.5 times 1 minus 0.5 divided by n. So n is the number of trials we ran, so since we spun the coin 20 times, n is going to be 20. Let's go ahead and just round that to 2 decimal places and see what we get. Alright, so that's going to give us 0.11. Now, using all that, we're going to plug that in to find our z-score. So we're going to have 0.35, that's our sample. Subtract that from our population. So that's going to give us the difference between our sample and our population. And then just how far off that is, we have to divide that by 0.11. So we're going to get a z-score of negative 1.36. Okay, now, before we move on, we're going to talk about how to do this in a more finessed, formal way. But I just wanted to ask you, knowing what you know about the empirical rule, is this z-score of negative 1.36, is it unusual or is it within your expectation? I would say because it's less than 2 z-scores away from what we would expect, okay, which would be p naught, I would say it's probably typical, okay? So I would say if I spun a coin 20 times and 7 times it comes up heads, even though that's not a 50-50 split, I would still say it wasn't unusual enough to call unfairness on that coin. Alright, let's continue on with a couple more examples. So, suppose that 100 people attend a boot camp and 38 return to prison within 3 years. Okay, the population recidivism rate for the whole state is 40%. What we want to know is what's p hat, what's p naught, and what's our test statistic. So p hat is when we actually ran a study, what did we see? So when we actually ran the study, we found out of 100 people, 38 returned to boot camp. So p hat is 0.38. Our p naught is the status quo, that's the thing that we're testing against. So since the population recidivism rate for the whole state was 40%, that's our status quo. And something else I'd just like to add in here is that n is 100, so that's how many people we observed. Now, the test statistic, we need to find the standard error. So that is going to be, remember, we have to use p naught, so that's going to be 0.4 times 1 minus 0.4 divided by the number of trials we had, which was 100. Error of 0.05. Now, when we find the test statistic, which is z, we are going to have 0.38 minus 0.4 divided by 0.05, and our z-test statistic is going to be 0.4. Alright, so I just want to give you guys kind of an idea of what this looks like. So, our normal population of prisoners is going to have a 40% recidivism rate. Okay? Now, what we found when we ran our sample is we found 38%. And what we were thinking is we're like, hey, does this boot camp make a big enough difference that we can expect most of our samples to be around that 30%, 38% or lower? Now here's the deal. 38% is definitely lower than 40%, but is it statistically significantly lower? And the answer is no. It's not even a full standard deviation below. So I would probably say that this boot camp isn't having a huge effect on the recidivism rate. Now, formally, instead of just saying I feel like or it looks like, what we're going to get is we're going to get a p-value. Okay? What that p-value does is it measures the probability that the null hypothesis is true. Okay? So the null hypothesis in the top part, if we scroll up, so the null hypothesis for this example was that the boot camp doesn't do anything. Okay? Now, if our z-score is further away, what that says is, hey, your null hypothesis is probably not true. Otherwise, these test statistics that we're seeing would be very unlikely. Okay, so is the number that measures the probability that the null hypothesis is true and that our test statistic will have values as extreme or more extreme than the value that we actually observed. So here's where the p-value comes from, is first we have to find the z-test statistic. Remember, that's the z-score. Okay? And that's going to give us different p-values. And we're going to use that z-score table and StatCrunch to find them. So here's the deal. Is the probability of spinning a coin 20 times and getting 5 or less heads, okay, those have z-scores of negative 2.2, negative 2.7, and all that. That's a p-value of less than 2.5%. Also here, because these are greater than a z-score of 2, that's also going to give us a p-value of less than 2.5%. The reason is because remember, if I draw a normal distribution, most of the time I'm going to get 50% heads, and the probability I get 5 or less heads is down here in these tails. Okay. So, what we're going to do is we're going to skip this question and we're going to get on to writing the hypotheses and interpreting the p-value. Okay. So, it is believed that 45% of STEM majors are female. We don't believe this is accurate, so what we do is we take a sample of 300 STEM majors and find that 120 are female, so that's 40%. So first, the null hypothesis is that nothing has changed. So we still assume that status quo, that it's 45% female. And our alternative hypothesis, well, we just said we don't believe it's accurate. We don't know if it was, we didn't expect it to be higher or lower. We just thought it was going to be different. So we say not equal to 0.45. What this means is that what we're looking for is that we're assuming that the population proportion is still 45%, and we're looking for either very extreme low values or very extreme high values to disprove our H naught. All right, the next step is that we want to find the z-test statistic. So, remember, P naught, that's the thing that we're testing, is 45%. P hat, what we saw in our sample, is 40%. And then our standard error is going to be the square root of that 0.45 times 1 minus 0.45 divided by the size of our sample, which was 300. Let's just go ahead and round that to 2 decimal places. 0.03. So our z-score is going to be 0.40 minus 0.45 divided by 0.03, which is going to give us negative 1.67-ish. Alright, now suppose that using that z-score, we looked at our z-score table, and we found a p-value that was 0.0817. Okay, what we want to do is write a verbal interpretation of the p-value and how it relates to our population proportion and our statistic. So here's what we're going to say. The probability that, let's see, what does this say? 45% of STEM majors are female. Given what we saw in our sample, or more extreme values, is 8.17%. So another way of saying this is that the probability that H naught is true, and we saw what we saw in our sample, that probability is only 8.17%. Okay, so I'm going to stop the video here, and the next couple examples are going to be in the next video, as well as doing this in StatCrunch.